Okay. Hello, everybody. Looks like we've got not quite as many people as usual. I think people are in a different meeting and still coming in. So maybe we'll give it a few minutes. Hey, Scott, are you there?
Yep.
Can you make Alexander and Connor into on the panel?
Sure.
Hey, Alex.
Hi there.
Okay, waiting for Connor here.
Okay, I promoted them, just waiting for them to come on over.
Okay, so I think I'll just start then. Oh, he says that Zoom crashed when you did it. Okay, anyway, I'll let them take care of that. Okay, sorry for the delay, everybody. So we're starting a little bit later today than usual and probably not go quite as long. Let me share my screen again. Share my desktop. And I wanted to update you on some things that I did pertaining to what we talked about last time. I continued developing a little bit the programs that we had. So I would given you this project with the Fibonacci numbers, and I have put an updated version of that into the Dropbox folder that all of you should have access to. So let me just show that to you. Here it is. So here's the Dropbox folder, and I've got a folder here called examples, June 13, because I just set it up today. There are a few things in there that I'll refer to a little bit later on. There is also a folder called Fibonacci. Okay, and let me just show you what is in there now, because it's a little bit more developed. Okay, Fibonacci June 11th, because that's when I was working on this. So this is an extended version of what I had done last time. Okay, so let me just show you what I've done. I have completed the step that makes this kind of symbol. Okay, I suggested that you do that here. So what I did was I created a Fibonacci sequence, and then I applied modulo numbers to each of the entries in the Fibonacci sequence. Okay, and I told you that you should expect to see a figure that looks something like this down here in yellow. And I went ahead and did that. This is with modulo 10. So that looks pretty cool. It's kind of like the cover of some metal album, right? And you can play around, and some of the numbers that you use for the mod give a fairly messy, random sort of looking thing, but some of them look pretty cool. So here's another one. Here's mod 25. As you increase, they look kind of crazier and crazier. Here's mod 26. That's also one that I thought was pretty cool. And you can do mod something really big. Here's mod 50. Maybe I should play the slides. Okay. So you still see a pattern. It's got left-right symmetry to it. And here's mod 250 if you want something really cool. Actually, I turned this one upside down because if I do that, then it looks like it kind of is a face. If I stare hard enough, kind of a creepy face. Okay, so I think I didn't put the code for this into Dropbox yet, but I put the earlier version of the code here in this Fibonacci folder. And I'll go ahead and add this one with the cool diagrams afterwards so that you guys can work on that and develop your own version of that. Maybe I should take a few moments to just show you the elements of that code. There are some new things in there that you guys can play with. And you might need a little bit of background and just a little bit of trigonometry and so forth. So here's the step where I apply, if everybody can see, I apply modulo something to each of the elements of the Fibonacci sequence. And I hope it's reasonably clear what the logic is here. So this mod num is the mod that I'm applying. I'm going to make a new list that's going to contain the elements of the Fibonacci sequence, but with mod applied to each element. And here's the for loop that does that. So I append to this empty list here. I append with the dot append command here. By the way, can everybody see my cursor and the stuff that I'm highlighting? Is that working? Complete? Okay. Just fibs, whatever entry I'm looking at, mod num, right? And fibs was the original Fibonacci sequence that I set up. I found that it was useful actually to start the Fibonacci sequence, in this case, with 0 and 1 rather than 1, 1. So that I think is different from what I showed you last time. So make sure you're aware of that if you're trying to follow along what I did here. There are a few other things. So when I made that shape, I needed to make basically a list of points going around a circle. Okay, around the edge of a circle. And I want them, basically, I want to have, for example, for this, it would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then last number here should be the maximum that you see in the modulo of the Fibonacci sequence. Okay. So what you need to do is find the max of the Fibonacci sequence and set up a set of radially positioned points. And that's what I've done here. So maybe see if you can figure out that and ask me if you get stuck. And then you have things like this. So there's a circle command that comes from PLT. So this thing that I call circle 2 is circle, and then the input is coordinates for the center of the circle, and then a radius. The radius I set up here, I've set it to be equal to 1, sort of arbitrarily. Then you have some options like color. I made it B for blue. That's why there's a circle here, because I basically want to see where these points are in the circle. And then I made a plot of all the points connected by lines, and I made them brown. Okay, so again, that's something for you to play with. I put other materials relevant to what I talked about last time. Let me show you those. In this examples folder, June 13 examples folder, you see something called Fib Giver. And that is just a very simple version of the Fibonacci stuff. So I want to make sure, since I know that everybody's coming in here with a somewhat different background, I want to make sure that there are things that are useful to people at all different levels. So if you're struggling to understand exactly what I'm doing in, for example, the Fibonacci code that I just showed, maybe try this simpler version that's only a few lines, this Fib Giver. It's just a simple function. So it's an example of the kind of function that I described when I just taught you what functions were. But it gives you, it returns a list of numbers that are the Fibonacci numbers up to some maximum value. So max fib is the maximum number of entries in the list here. And so if you're, again, struggling, maybe open up this file and make sure that you understand the different elements here. This should be a starting point for you to understand the other code that I was talking about. Okay. Other things that I've put in here, this ISBN read is related to that example that I gave of a data integrity test. Okay, here is the International Standard Book Number test, which I discussed in some detail last time. And I just polished the code a little bit. I left it as an exercise for you last time to develop your own. So now you have something that you can compare with. It's called ISBN read. It's right here. Okay. And here's what it looks like. I actually added some more books that you can play with. My list of favorite books. And this is a good way to get used to manipulating lists. Okay, so make sure you understand what is being done with the lists here. This is a fairly straightforward set of commands here that should be good for exposing you to those things. And again, ask if you have any questions or if you want to get access to any of these books. Okay, what else? Okay, there's the Celsius to Fahrenheit little Python script that we discussed last time. Here are the actual lists of books. Okay, you can add your own, make a database of your books and check that you've got all the ISBN numbers correct. It's critically important. Parabolas, I'll talk about that in a few minutes. Okay. Okay, any questions about that?
Nothing so far.
Nothing so far. That's good. Okay, so I thought I would move on to a physics project or a list of physics projects, partly because that's what I'm more used to teaching and partly because it's the obvious next level in complexity. So we're going to go beyond cryptography and playing with series and sequences. I've got two projects that I have in mind for you guys to work on, and I'll spend pretty much the rest of the time describing what these are. One of them is something we sort of already talked about, which was the projectile motion problem. I use that as an example of how to set up your own workflow diagram, which I think is important. I kind of belabor that a lot. When I teach this class, I make everybody do that themselves. This is kind of a fun project. Here's a picture actually of the Paris gun, which in World War I was a giant cannon built by Krupp's Armaments to shell Paris from 75 miles away. And it was the highest reaching projectile produced by humans until the invention of the V-2 rocket. So that was pretty cool. It was high enough that they had to start to worry about things like the Coriolis Force. So to get some perspective on that, here's a picture of France I took from Wikipedia, and then Paris and the location of the gun. So they actually had a cannon that shot all the way over there and pretty much rattled the Parisians. Here's actually a model of what, it's not an actual photograph of a gun like this, but a scale model with the trees and stuff to give you some perspective. And the shells were about 234 pounds. So it'd be kind of like you're firing a bunch of college football players at Paris. Okay, so first step kind of talked about was you want to say where is going to be the location of the 0th coordinates at time equal to 0. The obvious thing is to say, let's make time equal to 0 be when the cannon comes shooting out of the, when the shell comes shooting out of the cannon. Okay, by the way, it's mounted on a railroad. I hope you can see that there's kind of a train here. And here's the cannon. So again, that just gives you some perspective on this gun. And we need to build up our thinking about this. So that's why I'm belaboring this. I want to mimic what one actually does when doing a physics project computationally. Okay, and then we have a vector. If you're not used to vectors, don't worry too much. You'll hopefully be able to develop some intuition of what I'm talking about if you just watch. Okay, it's a vector representing the initial velocity given to this shell as it comes flying out of the cannon. And it's got also a velocity going along the x direction that I've sort of arbitrarily chosen to be horizontal, and in the y direction as well. The I hat basically just is a symbol to mean x component. The j hat is a symbol to mean y component. So that's the amount of velocity up and the amount of the velocity horizontally. And okay, by eyeball, it looks like the angle that they're shooting at there is roughly 45 degrees. So I've labeled it. Okay, and then when I introduced this earlier, I said if we wanted to write a program to say, you know, what is the trajectory of one of these projectiles, we'd have something like this. And I talked about setting up a loop. You guys have worked with loops now in the discussion of, you know, the Fibonacci sequence and so on. So I hope that if you didn't have a good handle on what I was talking about before, when I discussed this picture, you do now. And we said, okay, we need to say what are some initial constants. We start the loop. We have to figure out whether the time actually makes sense for us to proceed with this program. And if the answer was yes, then we did a calculation. So now what I want us to do is take this diagram and expand it out to discuss what we actually need to do to fill in. Maybe let me open up my laser pointer. This square right about here. Okay, we need to fill that in. So we'll need to expand this diagram even further. And to do that, we need to go and look at some basic physics. Now, again, I understand that everybody's coming at this with a somewhat different background. So I'm going to try to meet about halfway in terms of what I think people probably have experienced. So to understand projectile motion, you basically have to understand kinematics, that is, how the position of something changes with time in 2 dimensions. So an x position and a y position. And in the case where you have a constant acceleration. So if you have something in free fall, if you have a body moving through the atmosphere, for example, and you ignore effects like wind resistance and so on, and you only have the effects of the gravitational field close to the surface of the Earth, then the acceleration is a constant, and it's always directed toward the ground, toward the surface of the Earth. Okay. Now, in general, if you've got a constant acceleration, these are the kinematical equations telling you the position along an x direction as a function of time, and a position along the y direction, which we usually think of as being up and down just by convention, as a function of time. In terms of an initial x position or an initial y position, an initial velocity or speed in the direction of x. Okay, so v subscript 0, the 0 means initial. The 0 always means an initial value. And then the x superscript means the x component. And if there's a constant acceleration, then there could be an x component of acceleration, so an a subscript x, and an a subscript y for a y component of a constant acceleration. Now, if x really is the horizontal direction along the surface of the Earth, and you don't have any other force other than gravitation close to the surface of the Earth, no friction or anything like that, then the x component of acceleration is not going to be there. It's going to be 0. And the y component of acceleration is going to be, well, whatever is known and measured, which happens to be a negative 9.8 meters per second squared, if the positive y direction is chosen to be up. Okay, we call that g. Okay, so if that's the position as a function of time, the velocities as a function of time, the rate of change in the position as a function of time, for both the x and the y components, are given by these expressions. And if you've had calculus, then, well, the velocities are just the derivatives, the first derivatives with respect to time of the position equations. And if you haven't had calculus, don't worry too much. You can just take these as equations given to you. The prime means take the derivative with respect to time. Okay, and again, if there's no acceleration horizontally, then this term will be 0 and will not be there. And the velocity in the x direction will just be some constant. Okay. And just as a notational thing, delta x means the change, for me, will be the change in the x position relative to the initial x position as a function of time. So x minus x initial. So delta means a change, same for delta y. And finally, just as something that can be useful, I have written how you can relate the velocities as a function of displacement rather than as a function of time. Okay, so to do that, simply eliminate between these two sets of equations the time, and you get an equation like this. Okay, so for the specific case of an object in free fall, like a projectile, a cannon shot out of, a cannonball shot out of a cannon, or the slug shot out of the Paris gun, then those equations reduce to the following. We've got the y component of position as a function of time, the x component of position as a function of time. It doesn't have any acceleration, so again, we don't have any term corresponding to acceleration. And for y, we have a negative g acceleration, where g is 9.8 meters per second squared, or if you prefer, 32 feet per second squared. So these are the fundamental equations that you need to write down, right? And I'm just going to give them to you. This would be the step in the process where you sit down and write out everything that you know and that you can use. Okay, so the project then, well, it's just another version of the Paris gun, but I'm giving you a specific case, you know, just to have something more concrete to work with. Your project is to imagine that you work for a computer game company and you've got a computer game. I think this is an actual computer game with some creatures shooting ball lightning at each other. I've never actually played this, but I think it's something you can play on maybe an Android. And you've got a protagonist of your computer game running around here with this kind of zapping light ball gun, and you can shoot it, and he's supposed to shoot these things like this little monster here, or maybe this monster. Okay. Now, say that that the velocity of the thing coming out, the say the ball lightning, or whatever kind of projectile it is, say that it has some fixed velocity, magnitude of velocity, initial velocity that's just dialed in. And then what you choose with your joystick is an angle at which to shoot this thing. Okay. So as you're playing the game, you're basically changing the angle here, changing how the gun is positioned, such that you want to hit one of these monsters. And so the computer has to read in the angle and say, did you position the gun in such a way that you actually hit the monster? Or maybe more specifically, something like this. Okay, so here again, I'm drawing pictures. All right. We've got some angle, we've got some velocity. Let's say that this guy is trying to hit this monster right here. Okay, as usual, we have to say what is x equal to 0, what is y equal to 0. So in order to establish that, I've drawn a picture. Remember, always draw a picture. That these things that people sort of shrug about, they're often the most important. I've drawn a picture and I've located the 0 point in this axis right at the position where the ball lightning is zipping out of the gun. And I've drawn an arrow for velocity. Oops. Okay, so this is your starting point. You need to take that set of equations that I gave you and solve this problem. So again, repeating what I just said, start by assuming that the initial speed, the magnitude of the velocity is fixed, and say that you know, excuse me, you know the initial position of this guy, this monster. Okay, it's on the picture there, so presumably inside of the computer program is a coordinate, a delta x along this direction and a delta y along this direction, indicating the position of this monster. So you know the velocity and you know the delta x and the delta y. How does the computer know whether you found the angle that hits the monster? So basically you need to find the angle which hits the monster. Okay. So one thing you need to do is complete this diagram, this flow chart, this workflow diagram by filling in, by filling in this calculate delta x, y, or excuse me, this x, t, y, t box here. Maybe make another page and fill in what goes into here. Okay, and try to follow all the principles of good project design that I have highlighted so far. And if you want me to look, I can look and make comments on what you've done. Finally, you want to make a graph. So at the end, you'd like to be able to see a trajectory drawn like this and verify that it actually does hit the coordinate that you want it to hit, namely where the monster is sitting. Okay, so the first thing you need to do is this step. Well, these two steps. I've sort of gotten you started on the first two steps. You need to figure out how to take delta x, delta y, and v0 and translate it into a theta. Okay, once you've got a set of equations that can do that, you can substitute into the computer program. Okay. And just to give you a preview of what you should find, here are some trajectories. So I imagine the protagonist of this video game right about here, where this black dot is, and the monster is right about here. You should basically find two types of solutions to this problem. Angles that sort of go directly toward the monster, and another set of solutions that pop up and then fall down like this. And once you get far enough, you can maybe make some cool graphics. So I have done that. And let me show you what I did. I need to open up my folder. So you can even make an animation of the ball going up and coming back down to hit the monster. So I imagine the monster right here. And this is kind of what it looks like. Or if you want to see within the code itself, here's what I have. Stop everything so I can make it look good. Okay, you see here what I've done is I've plotted the trajectories of, well, two different trajectories that both hit the monster, right? They both hit the same point. But I see that one of them gets there faster than the other one. So I can even figure out which trajectory I should use if I want to hit the monster before he's got a chance to scuttle off. Okay, so you probably saw as I scrolled through here that there's a lot in here. And I don't mean to scare you with that. You can work your way up to it. But you should have noticed that there are some neat visualization things here. So for example, I arrayed a bunch of plots in a 2x3 array here. So six plots in one array like this. So that's something you should try to figure out if you can do yourself. I put a bunch of plots on the same graph, a bunch of curves on the same graph. So these are things that you should look forward to. And I can put my code up into Dropbox after you've struggled for a little bit so that you can look at what I've done. But I suggest trying to figure it out yourself a little bit before I jump in. Okay. Now again, if you're having trouble following along, if I'm going a little bit too fast, I've got some suggestions. One is this parabola. Have a look at this parabola notebook that I have in Dropbox. So in examples, June 13, 2021, I have something here called Parabolas. Okay, this is if you just need to get used to typing in, say, a parabolic equation and making a plot. You know, if the rest of what I've just discussed is too overwhelming and you need to slow down a little bit, go ahead and open this up and make sure that you understand what's going on there. This will show you, again, how to make basic plots. Here's the content. So you see I'm importing various libraries. And I've defined a fairly simple quadratic function. So define def y versus t. And what this is essentially an equation like this one, the y and t here. I just plugged in some numbers. And then I've shown you how to make a plot. Okay, one thing to notice is that I've made an array of times from 0 to 11 in steps of 0.1. Imagine that they're in seconds. And notice that I've made the y vals. Y vals are the values of y that I want to plot. All I did was give the function this whole array as an argument. Okay, that's all I had to do. So that's pretty nice. And then I made a plot. So if you want to go slower, maybe see if you can just expand on what I did here. Instead of doing y versus t, for example, you can try to do y versus x. You can do x versus t, maybe take all the different combinations of kinematic equations here and just play with making plots. Maybe write a version where you can give, say, the coefficient of the t here as an argument of the function. These are all little exercises that maybe you can do to build up to this ball lightning program over here. Okay, so I think what I'm going to do now is let you guys first try to get started on this. So the first really the first thing you're going to need to do is find this equation for the angle. So take out a piece of notebook paper, find the equation for the angle in terms of delta x, delta y, and initial velocity using the set of equations that I gave, and integrate that into this diagram this flowchart diagram. Once you have had a chance to do that for a while, we'll discuss how that works, but I want you guys to try it yourself. Or if you need to step back and work on something like this, this is also okay. And to help everybody get started, again, I have put, at least I think I did, in Dropbox, if you go into the Projectile folder, I have put that slide with all the kinematic equations so that if you need to have it sitting right next to you while you're typing into the Jupyter Notebook, you don't want to be flipping through my slides, you've got it right here. Okay, so I think maybe give you about 15 minutes for that. Does that sound good? And then we'll end with some other comments and we can pick up again on Friday. Okay, so for what you want to do right now, see if you can write down an equation, an algebraic equation. Don't even type anything right now, but see if you can write down an algebraic equation that relates theta, the value of the angle that hits the monster, given the initial delta x, delta y, and v0. Okay, is that clear to everybody? So it's this right here. Start by assuming that v0 is fixed. What angle is necessary to hit the target? Maybe I can add some annotations here if that's going to help. given V0, what and delta X and delta Y, what is theta that it's monster? Okay, then once you've got that, you'll know what to type into the Jupyter notebook, say if you want to make plots and such. Okay, somebody asked, how was the relative rate of movement of balls across the two trajectories determined? Is the ratio of their velocities in the animation the same as that of the actual magnitudes of the velocities chosen? Okay, so in the animation that I showed, so first of all, you're given a magnitude of initial velocity, right? And you're given, so put it here, you're given an initial magnitude of velocity, and you're given, and you're going to have some theta that you have to figure out. And once the theta and the initial magnitude are determined, then x of t and y of t are determined. Okay, so that means that for each step in time, if I have a list of time intervals, say in seconds, 0, 1 second, 2 seconds, 3 seconds, so forth, I can plot x for each, x and y for each of those. Okay, and then when I make the animation, all that's happening is I'm showing that position as a frame in the animation. Each position is showing up as a frame in that animation. Okay. So once you really have figured out that equation, once you've figured out what theta needs to be, you've basically figured out everything you need to set up that animation. So the next step after that, to build up to the animation, what I would say is make a plot of x as a function of time and y as a function of time. Okay. And I would urge everyone to not try to go too quickly, and maybe take the time between today and the next meeting to polish whatever it is that you're doing and see if you can understand everything that's going on and formulate any questions when you get to something that you really can't understand. By the way, just to give you some foreshadowing, here's what my next stage in my workflow diagram looks like. Maybe see if you can come up with something like that.
Somebody's asking what value of G they should use in their simulation.
9.8 meters per second squared. Or if you want something more precise, just Google what G is in your particular geographic region. Or you could try doing it on the moon and use something else, right? Figure out what G is for the moon or on Mars. If you want to shoot the Paris gun on Mars. And if you don't like thinking about monsters, like stupid little monsters in video games, you can imagine this to be an Imperial German soldier and this monster right here to be the Eiffel Tower. Now, when we get farther along, we might want to incorporate other effects, right? Especially for something like the Paris gun, constant acceleration motion is not going to cut it, actually. You've got air resistance, you've got the Coriolis Force, and all these sorts of things. But this is how these kind of things work, right? You start with the absolute simplest description that you can think of, make sure that you've got a handle on that, and then you build on top of that. And that's how computers are useful too, because much of what we're doing here, you can actually work out to a large extent on paper. I mean, making the plots and so on, for that, it's nice to have the computer, to have the Python, and for making animations, it's nice to have the Python. But if you want to add a term in these equations that accounts for, say, linear or quadratic drag coefficient, then having the computer calculation is nice, and you can see that you recover the parabolic motion as you sort of gradually turn on and turn off the air resistance and the drag. And then even beyond that, you can layer on additional effects, right? So going forward, if we really had a lot of time to work with this sort of thing, one of the next things I would assign would be
I have a brief question. Will you be showing the solutions for the equations? I assume.
Oh, yeah. Yeah. So I was planning on, I thought today we would have 2 hours. We actually only have one, but my initial plan was to let everybody try to find their own way through these equations over the next 15 minutes or so, and then I would go through the derivation myself. So I'm still planning to do that. It's just that we'll probably have to pick up next time rather than doing it all today. As we speak, I'm also updating my PowerPoint slides, and I will put them also in Dropbox to account for the changes I've made today. Today is June 13th. Okay, so just updated my slides there.
Somebody's asking if there's a specific initial velocity that they should use.
That's a good question. I don't suggest anything particularly significant. I'd say just try a few values. I can tell you what I have in some of my figures here. So I have, if we're thinking 9.8 meters per second squared, I've got a del x of 595, del y of 60, and v0 of 100 meters per second here from whatever it was the last time I ran this. So that's something you can try. By the way, say that you are working on this kind of thing and you find that you really don't understand some of these functions. So what I would do is I would just copy, say import, say you want to make plots and you just don't, you realize you don't understand how PyPlot works. So I would say copy this line. And then there's this amazing thing called Google. Paste it into Google. Like the first thing that comes up is PyPlot tutorial. And in PyPlot tutorial, you can see tons of examples of things. So for example, how do I make the things that I plot appear as round red dots? Okay, here we go, comma R0. So if there's anything that I've shown you and you're just scratching your head wondering what to do, here's another example. There's a green triangle. Okay, just try copying the line out of the code and putting it into Google, and you'll often find stuff like this showing you exactly. Making multiple figures, putting them together. All right, if you're seeing these kind of figures and wondering how the heck I did that, you're wondering about colors, things like that. So there's a question here. Do ranges with specific step values always result in continuous plots? So I'm not sure if I'm interpreting that question exactly the way it's meant, but let's go back and look at these plots and ask what's actually happening. So what you're actually plotting is a whole bunch of points, right? And what is shown is those points plotted and then connected by little lines. Okay, so it looks continuous because you've got a whole bunch of points close together connected by little lines. But of course, it's not really continuous, right? So one thing that you really need to do as you're setting this up is figure out how close those points have to be. All right, if they're not close enough, then your plot is going to look like a bunch of lines with kinks in them, right? A bunch of straight lines connected. Okay, so that's one thing you need to mess around with. When you make your plots, if you accidentally make the steps too large, you'll get something that doesn't really look quite like a parabola. It'll look like a bunch of sharp straight lines. And then you need to figure out how to make the steps small enough that it doesn't look like that anymore, right? Does that help? Okay, if you want points not joined by lines, you could do something like, well, let me try something here.
Just so you know, you're not sharing screen right now.
Okay, just a second. My computer's freezing here.
Isn't there a scatter plot function that is by default has no lines connecting the points?
Yeah, but you can also just change the symbol that is used, and
Yeah.
it's just taking me a while to do it. Okay, so here, here's an example, but I need to share my screen here. Okay, so here's that Parabolas notebook again, and all I did was put a dot inside of the plot thing here, and you see now it's not a continuous thing. The other thing I did is I have time steps through by steps of 1 rather than 0.1. So if I did 0.1 again, then I have a bunch of dots that are really close to each other. And if I take this dot symbol outside of the pie plot thing here, then they're all connected by lines, and I get back to the continuous looking thing that I had before. Okay, so that's how you do it. And as Connor says, there's also a separate scatter plot function. This is how I would do it. Now there's very few points. Okay. Okay, so unless there are any other pressing questions, I think we'll adjourn for today.
There was one question now. What are some of the next steps if we finish the main exercise?
Oh, okay. Well, if you finish the main exercise, I actually have a list of extensions here with a range of things that you can do. So well, there's some simple things you can do that probably shouldn't take much time. So if instead you are given the initial angle and you have to dial in the velocity, maybe redo the code that way. Okay. That should be pretty straightforward. If you've got the velocity given the initial speed, or excuse me, if you've got the angle given the initial speed, then it shouldn't be too hard to do it the other way. Also, examine x versus t and y versus t. Okay. Now, once you've done all of this, you can try to figure out how long it actually takes to hit the monster. And then you could ask well, how likely is it that, say, in the video game, the monster is able to scurry away? How likely is it that you'll actually be able to hit the monster before they're able to scurry away? Okay. One thing that you should find is that there are 2 trajectories that hit the monster, or hit Paris, depending on the context. 2 trajectories that hit the monster, given an initial delta x, delta y, and v0, and maybe you need to figure out which one of those 2 solutions is actually the better one. Okay, and for that you need to find out how long the thing takes to hit it. And finally, I would say make this kind of animation that I showed you. That takes a little bit of, messing around with the code. I would use this animation function. This is what I use. See if you can export it into, say, an MP4 file that you could show online. And if you really want something else, try adding other terms that take the acceleration away from just the constant case. This is just a list of things that you could try. Okay. Hopefully that is enough to keep you occupied, though, for now. And just to warn you, the steps that give you theta in terms of v0, delta x, and delta y will require that you use, say, the quadratic formula. That's why you got 2 solutions. And it will require inverse trigonometric functions. So you need to figure out how to use inverse trigonometric functions in Python. That, again, is something that you should be able to figure out by using Google. But as a hint, note that I've got import math here, and I've got math.tan here. So actually, let's do this. Let's copy math.tan and see what that gives if I just do a Google search. I can actually take out the theta, just do this. Or do this. So I get if I do math.tan Python, I get a bunch of nice documentation, mathematical functions in Python. And it gives me a nice list of different functions that you can use and an explanation of how they work. And yeah. Okay. Is there anything else that we should discuss before we call it a day?
Seems to be it.
All right. Well, thanks as usual for the attention. Hope you guys are getting something out of this. And not hesitate to ask questions. And if there's nothing else, then I guess we will see you on Friday. All right. See you, everybody. See you, Connor. See you, Alex.